The scale of the journey. At first glance, it feels like the stars are right there. You step outside on a dark night, and the sky looks like it's filled with shining neighbors. Many of them are brighter than city lights, some even seem almost within reach. The illusion is powerful. Your eyes are tricked into believing that the universe is small, that perhaps the next star could be just around the corner if we only knew how to get there. But the actual scale of the journey shatters that picture the moment we start to measure it in numbers. By 2025, we can describe those distances with far more precision than ever, and the picture that emerges is staggering. Let's take the closest case. Alpha Centauri is the nearest star system to Earth. When people hear that it's only 4 light-years away, they sometimes imagine that's a manageable figure, like driving across 4 towns on a map. Light-years, though, are not ordinary units of distance. They're the measure of how far light itself, the fastest thing we know, can travel in an entire year. 1 light-year is about 6 trillion miles. Multiply that by 4, and Alpha Centauri stands roughly 25 trillion miles away from us. That's not an engineering challenge like building a longer bridge or digging a deeper tunnel. It's a scale that doesn't fit within human experience at all. For comparison, let's shrink things down. The moon is the farthest any human has physically traveled so far. From launch pad to lunar surface, it's about 240,000 miles. Imagine stacking that distance over and over. To equal Alpha Centauri's stretch, you'd need more than 100 million moon trips in a row. Another way to see it is with the orbit of Earth itself. Our planet makes a complete lap around the Sun each year at a distance of 93 million miles. That orbit, if laid out in one line, would need to be repeated more than 270,000 times just to touch the edge of Alpha Centauri's domain. Even if we race the numbers against light speed itself, the story doesn't get much better. A light beam leaving Earth right now would take over 4 years to reach Alpha Centauri. That's the most optimistic timeline the laws of physics allow. For anything heavier than a photon, the challenge becomes overwhelming. The best spacecraft humanity has launched to date, probes like Voyager 1 and Voyager 2, crawl across interstellar space at around 17 kilometers per second. They've already spent decades moving at that pace, yet even at their remarkable velocity, Voyager would require more than 70,000 years to get to the nearest star. That's not an academic statistic. It's the raw time it would take inside the spacecraft clock. Think about how long 70,000 years really is. Entire civilizations rise and fall in less than 5,000 years. Written history covers only about 6% of that span. If one of those probes had left during the Ice Age, when mammoths still roamed Earth, it would only now be less than 1% of the way to Alpha Centauri. That's why every engineer and scientist working on interstellar concepts insists on starting the conversation with scale. If you don't first understand the raw enormity of the problem, every propulsion breakthrough sounds trivial, every cost comparison feels manageable. But once you lay out the raw math, you see why current methods can never get us there. There's also the psychological side of distance. Human minds adapt to measured space in relative ways. A person hears about a commercial flight of 12 hours and accepts it as long, but still tolerable. The same with a drive across multiple states, or even the months it took astronauts during the Apollo program to plan lunar journeys. All of those experiences give us a sense of confidence that long trips are possible if you organize resources correctly. But a star voyage cuts completely outside of that framework. It's no longer about long weekends or drawn-out expeditions. It's about time spans that far outstrip a human life, many times over. This difficulty is part of why science fiction stories often leap directly over the distance problem. They imagine ways of changing space itself, wrapping, folding, or leaping through dimensions. Those are narrative shortcuts, because in practical terms, traveling to another star is the slowest road humanity has ever imagined. If you scaled the Earth-Moon distance to the length of a single step, Alpha Centauri would be about the length of a daily marathon away. You'd be running all day, every day, carrying that step over and over again just to glimpse the nearest system. And that is only the first stop in a galaxy with hundreds of billions of stars. Now think about the resources tied to such journeys. Every rocket we launch today measures fuel in tons, payload in kilograms, and budgets in the billions. But when confronted with 25 trillion miles, numbers of that scale immediately collapse. You could launch rockets every year without pause, and they would barely move humanity toward the finish line. The curve of progress flattens into impossibility, which is why the question isn't about commitment or patience. It's about whether our technology can close the enormous gap between human ambition and astronomical reality. That's why Alpha Centauri remains a symbolic benchmark. It's not only the nearest known neighbor, but also the system with a confirmed exoplanet, Proxima b, orbiting within the habitable zone. It represents the shortest possible interstellar challenge, the easiest trip humanity might someday attempt. Yet, despite being the least distant target, it is still so far away that existing technology is essentially irrelevant for the job. Talking about Alpha Centauri forces us to confront just how unprepared conventional engineering is for this journey. By 2025, astrophysicists and mission planners have become increasingly blunt on this matter. Distances this vast cannot be overcome with gradual improvements in our current launch designs. You cannot stretch the lifetimes of satellites by another decade and expect it to matter. You cannot extend a mission budget slightly and expect meaningful progress. There has to be a fundamentally different way to cross space, one that works with the distances at hand rather than struggling against them. Grasping the scale of the journey does more than set the boundaries. It also acts as a guidepost for innovation. When engineers build propulsion concepts today, they know they are competing against hard numbers like 70,000 years by chemical rockets versus at least 4 years as a light speed minimum. Somewhere between those two limits must lie the technologies of the future, technologies that can shave tens of thousands of years down to centuries or even decades. The understanding of scale makes that search focused rather than blind. So while it's tempting to look at the night sky and feel that the stars are close, the 2025 reality shows us they are not even on the same map as human travel so far. Every mission we've flown to the moon, to Mars, to the outer planets, has been a local errand in cosmic terms. The stars remain whole continents away, and all of our most trusted methods of travel leave us stranded at the starting line. That is exactly why the next step isn't about launching faster rockets of the type we already know. It's about venturing into propulsion methods that can actually challenge the scale of the universe itself. The limitations of chemical rockets. When we think about humanity's journey into space, rockets are always at the center of the picture. They are the engines that carried astronauts to the moon, delivered rovers to Mars, and launched satellites that now shape everyday life on Earth. Without chemical rockets, space exploration would never have left the drawing board. They provide the immense thrust needed to overcome Earth's gravity, and for that role they stand unmatched. Every milestone we celebrate, from Apollo missions to the International Space Station, happened because we had these workhorses. But the bigger question is, can the rockets we know today reach beyond planets and into the realm of stars? Could the same technology that launched us across the solar system extend to another star system? Intuition might say yes, since rockets already cross hundreds of millions of miles. The truth, however, is that the physics behind chemical rockets places hard barriers that cannot be stretched to interstellar scales. The limitation is not a matter of effort, funding, or improvements in building techniques. It comes down to an equation first described in the early 20th century, known simply as the rocket equation. It is one of those deceptively simple relationships that is easy to write, but impossible to escape. The basic idea is straightforward. The faster you want a rocket to go, the more fuel you must carry. But that additional fuel adds weight, which requires even more fuel to accelerate, which in turn adds more mass, and the cycle quickly spirals out of control. It creates an exponential wall where trying to squeeze out more speed becomes impractical. Every engineer evaluating chemical propulsion eventually meets this same wall. It explains why we can launch to the moon, why we can cross to Mars, but also why a star mission under the same rules would fail. One way we measure the efficiency of any rocket system is through its specific impulse, called ISP. This value tells us how effectively a rocket turns fuel into thrust. For most chemical rockets, the ISP sits in the range of about 300 to 400 seconds. Even the very best examples fall into that same narrow zone, which is already near what the chemistry of propellants can allow. This means that the rockets we fly are not flawed designs waiting for better engineering. They are already operating close to physical limits set by chemistry itself. As one NASA scientist framed it, chemical rockets are about as efficient as physics will allow them to be. That point is crucial because it eliminates the idea that minor advances will unlock dramatic new performance. Chemical propulsion cannot be stretched all the way to the stars. To see why, let's scale the number. If you imagine a standard chemical rocket aiming toward Alpha Centauri, the nearest star system, the travel time is staggering. With an ISP of around 400 seconds, the math gives us a journey that would last roughly 50,000 years. That's 5 times longer than all of recorded human history. It is longer than the existence of many species on Earth. So even in the most generous scenario, such a trip collapses under its own timeline. Unlike a trip to Mars, where months of travel line up with human mission planning, a voyage of that length is meaningless to us as a species. No spacecraft can be maintained that long, no society can plan over such time spans. It stands outside the range of practical engineering. We can also look at real examples. The Voyager probes, built and launched in the late 1970s, are the fastest chemical rocket-based objects we have sent out of the solar system. They are now on true interstellar paths, leaving the influence of the sun. Yet even at their extraordinary speed, if pointed squarely at Alpha Centauri, they would require more than 70,000 years to arrive. When they eventually lose power, as they will in just a few years, their journey will continue in silence across the galaxy. A journey with no destination because of the overwhelming timescale. If Voyager does illustrate anything, it is that chemical propulsion can launch probes beyond planets, but not with any meaningful hope of closing the distance to stars. From the perspective of 2025, space agencies understand this with clarity. Rockets remain absolutely indispensable for leaving Earth itself and reaching orbit. No other technology can yet provide a concentrated burst of thrust like a chemical rocket, and that capability is non-negotiable for lifting spacecraft away from the surface. But once in space, their usefulness diminishes rapidly if the goal is interstellar travel. Agencies like NASA now treat rockets as the opening stage of a journey, not the complete system. They form the base, but they no longer represent the dream of carrying us across the stars. This distinction matters because it shapes where research dollars go. If chemical rockets could be re-engineered to gain orders of magnitude and efficiency, the problem would look very different. But by now it is widely accepted that chemistry has done nearly all it can. No matter how carefully refined the design, at some point the rocket equation tightens its grip. Instead, investments must move into propulsion methods that abandon chemistry entirely. This shift has already happened in planning documents and mission concepts. The stars require methods that bypass the exponential trap and scale with distance more effectively, whether through fusion, solar sails, or other exotic ideas still at the conceptual stage. There is also an important psychological angle to this truth. Since rockets took us to the moon, they inspire a natural confidence. If they achieve that leap, why not the next? But here the numbers resist optimism. You cannot simply scale the Apollo method to a larger target. The space between Earth and Moon looks vast to us, but against the measurement of light years, it is a fraction with no meaning. Believing that rockets will evolve into starships misunderstands the physics that underpins them. The laws of motion do not give ground to persistence alone. They need new ideas entirely. Some proposals try to bend the role of rockets back into interstellar concepts. They imagine colossal vehicles stockpiled with immense quantities of propellant, launched in stages or reassembled in orbit. But each of these ideas dissolves into mass ratios that collapse the mission before it begins. A ship that carries enough fuel to cross even a modest fraction of a light year would be so massive that no launch system could ever lift it, even with hypothetical global cooperation. The rocket equation does not leave room for a clever trick. It is absolute. So where does this leave rockets in the interstellar question? Essential, yes, but for a role limited to the start. They will always provide the brute force necessary to punch through the thick air of Earth's atmosphere, carrying payloads up to orbit where new propulsion methods can take over. Beyond that, though, they are not the engine that will ever take us to another star. Rockets are powerful tools, but for moving between stars, they cease to matter. And understanding why gives us a clear boundary. Every plan for reaching Alpha Centauri and beyond must leave chemical propulsion behind at the very first step. Fusion propulsion, harnessing the power of stars. For decades, humanity has been trying to answer the same question. Can we harness the same reaction that powers the sun and turn it into a propulsion system? Fusion has always been at the center of that dream. The process itself is well understood. Two light atomic nuclei collide at extreme temperatures and pressures, and in merging, they create a heavier nucleus, releasing energy. It is nature's ultimate power source. We already know this firsthand because it's happening continuously in the heart of our sun, producing the light and heat that makes life possible here. What makes the concept so attractive is its efficiency. When compared to chemical reactions, fusion releases millions of times more energy per unit of mass. That alone explains why it captures the imagination of space scientists. If you could ever package fusion into a rocket engine, interstellar distances suddenly become far less overwhelming. The tension is that while we can make fusion happen for split seconds in massive laboratory settings, we are nowhere near shrinking it into a compact, reliable, controlled form suitable for a spacecraft. Recent years have added new momentum to this field. In December 2022, researchers confirmed that for the first time a controlled fusion reaction produced more energy than was required to ignite it. That milestone, often called net gain, was achieved in the National Ignition Facility using powerful lasers to compress fuel pellets. By the standards of Earth-based laboratories, it was a narrow success. Net energy in, net energy out. But symbolically it crossed a barrier that had stood for over half a century. Instead of saying someday we will achieve this, we can now say we have achieved it, at least in controlled experiments. Between 2022 and 2024, further repeat demonstrations confirmed the effect under different conditions, showing that the principle wasn't just a one-time fluke. For spaceflight, those milestones don't mean we are ready to load fusion drives into rockets, but they signal a turning point. The basic physics is sound. The task left is engineering, and that path brings a very different set of struggles. To understand why this matters to propulsion concepts, think about what happens if you take that kind of reaction and redirect its energy into thrust. The most famous conceptual studies were Project Daedalus in the 1970s, and later, Project Icarus as a follow-up in the early 2000s. These were detailed design efforts led by teams of engineers and scientists, not science fiction writers. They sketched out spacecraft measured in kilometers, equipped with huge fusion chambers that would ignite tiny pellets of deuterium and helium-3. Each miniature burst of fusion energy would generate plasma, expelled through magnetic nozzles, pushing the vessel forward. In calculations, such ships could reach perhaps 10 to 15% of light speed. Suddenly, a 70,000-year trip to Alpha Centauri shrinks to under a century. In human terms, that is still enormous, but it is also a timescale that can be organized. a multi-generation voyage becomes imaginable. Today, in 2025, those designs remain on paper, but their legacy drives new studies. Various agencies have returned to fusion as one of the few propulsion modes that could actually cross interstellar spans. Fusion is compact compared to beamed energy sails or nuclear bombs exploding behind a plate. It has the elegance of using energy-dense reactions, governed by known physics, with a clear potential performance margin. The timeline, however, is a sobering one. Even optimists only suggest that laboratory-scale fusion drives may appear for deep space probes by mid-century. Some conceptual roadmaps tentatively draw the 2050s as a period when fusion-driven probes, without humans aboard, might actually leave the solar system at meaningful fractions of light speed. But here's the obstacle side. Every advance in fusion highlights the sheer size of the machinery required. On Earth, the test beds that enable net-gain fusion fill entire buildings. They require enormous magnetic fields from superconducting coils, cryogenic systems, and massive laser arrays. None of those things are remotely portable today. If you look at a diagram of ITER, the International Fusion Reactor under construction in France, you realize the scale. It is the size of a power station, with thousands of tons of hardware. How do you shrink something like that into a Starship engine? It isn't just miniaturization. It's about maintaining extreme conditions. Temperatures hotter than the sun's core, pressures that only advanced magnetic confinement can hold, and precise timing to ignite fuel pellets rapidly. Translating that into a system that can operate in space without constant technician maintenance is a challenge unlike anything we've faced. Weight adds another serious dimension. For spacecraft, mass is the ultimate currency. Even if fusion fuel such as deuterium is compact, the containment systems are heavy. Every ton of infrastructure launched from Earth multiplies costs and complexity. Engineers sometimes speculate about building such vessels entirely in orbit, using materials ferried aloft in segments, or even harvesting fuel from lunar deposits rich in helium-3. Those ideas are not physically impossible, but they stretch well beyond current capability. It means that even if fusion physics is solved perfectly, the engineering translation could still take decades more. You are not only asking, can we ignite the reaction? But also, can the ignition chamber survive tens of thousands of continuous bursts without failing? In actual spacecraft engineering, durability stands as high a hurdle as ignition. Despite this realism, fusion remains at the forefront of propulsion studies for one reason. There is no credible substitute. Solar sails accelerate too slowly for crewed missions. Antimatter, while hypothetically perfect, cannot be produced in the required amounts. Nuclear fission, although powerful, lacks the thrust-to-specific impulse ratio sufficient for true interstellar leaps. Fusion balances feasibility with performance. It is not easy, but it is possible within the laws of physics and does not require exotic materials that we cannot yet imagine. That kind of credibility matters as agencies and think tanks map future starbound probes. An example shows this balance. Imagine a probe launched in the 2050s using what some designers call an inertial confinement drive. It would carry thousands of tiny fusion pellets, each ignited many times per second by advanced lasers or magnetic pulses. The expelled plasma would drive exhaust velocities measuring in tens of thousands of kilometers per second. At a fraction of light speed, such a probe could plausibly reach nearby stars within a human lifetime. To keep the system stable, it would require automated repair systems, magnetic fields stronger than anything today's spacecraft carry, and continuous onboard power just to keep the confinement systems running. No one has built such a machine, but no one has proven it is impossible. That is the difference separating it from pure speculation. It helps to imagine the moment when a small test platform, perhaps not much larger than a car, demonstrates a sustained fusion pulse drive in orbit. That demonstration will be the milestone everyone watches for. Right now, fusion propulsion is a sequence of models and laboratory physics. By the mid-21st century, if progress holds, that line may finally be crossed. In that sense, fusion propulsion has advanced beyond fiction. It is no longer a poetic dream of bottling a star. It is a rigorous engineering pathway, lined with known problems that have possible solutions. The dates are long, stretching into the second half of this century, but the direction is no longer vague. For the first time, interstellar propulsion by fusion is seen as a roadmap drawn in pencil, ready to be inked when the supporting technologies fall into place.